Hello, my name's Associate Professor Benjamin Holcomb, and I'm coming to you here from the Dynamics Lab, again at UTS in the Faculty of Engineering and IT. This is a video about rotating machinery vibration measurements. It complements a video that I recorded some time ago where we looked at this particular rotating machine here, a 3-bladed fan, which was instrumented with a tachometer, which I've got sitting over here today on a tripod. Previously I had it mounted to the front of the fan blade. On this fan blade over here you can see a strip of retroreflective tape that every time this fan rotates and passes in front of this tachometer, we get a pulse in our measurement system to indicate once per revolution. That's how a tachometer works. I will be using today Siemens Simcenter Testlab acquisition system, and two particular packages that I'll be using from that system are impact testing workbook. I'll also be using signature testing advanced. We'll have a little look initially at signature testing advanced, because this is the work package or the workbook that is used, the solution that is used for making measurements where we're interested in tracking, for example, vibration with respect to a particular order of a rotating machine frequency. I've created a project earlier on Simcenter, and I'm just going to start it going so that we can actually see. It's a little bit noisy actually. I think we'll go for the slower of the 3 speeds. So over here you can hopefully see that red beam now that I've started Simcenter. I've got an output channel, an input channel here from the SCADAS mobile acquisition system that is going to my tacho. That's actually got an IEPE conditioning associated with it, and that's how this tacho works. So it takes IEPE signal conditioning from the acquisition system. I've got 2 other channels connected to this V8 acquisition module here. These are vibration channels, volts and IEPE. On one of those channels I've got an impact hammer, a modally tuned impact hammer, and I will reveal why in a few moments. That is connected onto channel number 1 over here, and on the other channel, channel number 2, I've got an accelerometer which is currently mounted to the frame over here of the fan, and that can measure the vibration of the frame as the fan rotates. I've got other videos where I demonstrate how to effectively do modal impact, how to calibrate accelerometers, how to verify the measurement chain, so I'm not going to be spending time on those particular things today. We'll assume that everything is already calibrated, that we know what we're doing with modal impact and so on. As I mentioned, I've started the signature testing advanced workbook. Here those 2 channels are defined. In fact, I'm only using one of them, of course, for the rotating machinery measurement, channel number 2. If I jump into the tracking setup workbook, here you can see that as a result of, I've got another screen up here, so maybe it's visible on this screen up here. As a result of the tachometer and the once per rev pulse that's generated every time that piece of retroreflective tape passes through the path of the beam from the tacho, I get a pulse in that signal here, which if I zoom out a little bit on the time axis, hopefully you'll be able to see those pulses passing through. It just takes a while to redefine the tacho bandwidth. So now there are some very nice pulses passing through in front of the display here, which hopefully, despite the intensity of the displays, is visible in the video recording. And so knowing the time between, or determining the time between those pulses, allows me to extract the RPM, which is about 1252. In the other video that supersedes this one, I also demonstrated how to use this stroboscope to be able to visualize the passing of the blades, and so I'm not going to go into too much detail on that, but I will just tune the frequency of the flashing of this light down to approximately 1250 RPM. And if I get that perfectly synchronized, it does send you'll notice that it sent my RPM measurement with Simcenter completely haywire, because there's now a lot of light coming back into the tachometer, and it thinks that that's the reflection of the red laser beam, but actually it's obviously the extra light from the stroboscope. In the frame of the camera now, hopefully you can see there that piece of retroreflective tape just I'm struggling to freeze it perfectly. It's just going a bit too quickly. I'm trying to get it so that it's appears to be frozen, because we get one flash per rotation. It's a bit tricky because I don't have a way to define that frequency on the stroboscope that's perfect. I'm just doing it with a fine, so there it is, approximately there. It's just gone past. I'm at exactly 1250, and then unfortunately this dial's a little bit sensitive. So you can see it sort of jumped to 1000 RPM there really quickly. And I've also dimmed the lights in the laboratory, which means that this video is a little bit yellow in appearance. I've turned the exposure up on the camera to try and counter the fact that we don't have a great deal of light in the lab, as a result of dimming the lights, to be able to hopefully freeze this motion in the camera. So it comes past quite slowly when the two frequencies are pretty close together. There it is just now. If I get it perfect, I can just stop it essentially and bring it back, and then it's just sitting there now, and then it jumps. I'm going to turn this one off because it does cause problems with my RPM measurement, which is now much more stable. What I noticed when I was setting this up previously was when I hit stop here, and it may be possible to see this in the camera, at some frequencies, when the rotating fan blade, which is inevitably misbalanced, coincides with the dynamics of the frame structure here, I get some extra vibration over here. So I took my impact hammer. I thought I want to know what those frequencies are. So I started the impact testing workbook. So if I come back into here and go to structures acquisition, do an impact testing, I'm going to strike the frame of the fan on the right hand side over here. I'm going to start from a completely new project here, which will take just a little bit of configuration. Let's just take a moment to negotiate a connection with the front end, set up the channels, determine which channels are powered, etc. So if I go to the channel setup worksheet, I'm just going to do this very quickly. Turn these two channels onto IEPE, ICPE. One of them, channel number 1 is the reference, and that's a force measurement. Channel 2 is an accelerometer measurement. I'm not worrying about the sensitivities and so on. We're really only interested in the frequencies today. Go to the impact scope workbook. I think my frequencies are relatively low, so I'll set an upper frequency limit, maybe actually of around about 512 hertz, and that will give me a frequency resolution of half a hertz, 2 seconds. If I go to the impact setup, I can start the scope, do a couple of impacts. I'll do them over here, try and stand out of the way of the video. So I'll stop the scope. So the trigger settings have been suggested to be able to effectively capture these impacts. That's working quite nicely. You can see I've taken a soft tip because this is a low, these resonant frequencies of interest are relatively low, I believe, so in the order of tens to hundreds of hertz. So I've chosen the silicon tip, and you can see the pulse width is quite wide. In the windowing workbook, or sorry, the bandwidth workbook, I can do some impacts now, and it's not a brilliant impact, and it's not a great structure to do measurements from because obviously it's an assembly, there's lots of loose connections and various things, but I'm getting some energy into the structure. Actually I'm using a bandwidth that's too high. I should have used a bandwidth that was the same as that which I set up in the oscilloscope, which was 512 Hertz. If I'd chosen to use the scope settings, that would have been more sensible. Let's do that again. So there you can see I'm getting energy into the structure. That was a little bit of a double impact. But there are already some quite nice peaks in here in the response measurement, especially around about 150 or so Hertz. So that's looking quite promising. If I come back in here and set some windows up, I'll be able to do, I'm already getting quite nice output with a force exponential window, so with a rectangular window. So if I do an impact, it's measuring for 2 seconds, get some audio feedback. The response decays very nicely to 0 by the end of the 2-second acquisition. The force window, the impulse force is already finished well in advance of the end of that window. It does suggest a force exponential cutoff. So I'll typically, if I've done a clean impact, I'll apply the selected settings. And then we can go to the measure sheet and do a measurement. So I'll just do 3 averages. Start that measurement. You can hear the audio feedback. And that's a reasonable impact there that you can see the impulse in the top left, the PSD for the impulse, the response top right, and frequency response are the PSD, and then the instantaneous FRF here in magnitude and phase, and the average FRF over here, which for the first impact is clearly the same as the instantaneous, and a coherence function which is essentially just 1 across the entire spectrum. I don't see meaningful coherence until I do a second and third impact. And there you can see I've got quite nice coherence. So I've got good signal to noise ratio on the 2 channels, and I'm getting good signal across a relatively wide frequency range, with the exception of that anti-resonance there. So my coherence is a little bit low at this location, and higher up in the spectrum perhaps I'm not getting as much energy at those frequencies into the structure. It's not a very nice looking FRF that we might be used to seeing from single components like cantilever beams and plexiglass plates and other such structures. But importantly, the coherence is very clear, and so some of these frequencies here that have been identified are regular or a valid, legitimate, like local resonances. And I can see that there's one around here at about 150, maybe a couple more, 153 Hertz. I've identified one here at 11 Hertz. There's another one at 38.26 Hertz. And I can see these frequencies when the fan runs down from its operating speed to 0 as it coincides, as the misbalanced fan that's had a few dings and dents taken out of it. It's clearly very misbalanced. It coincides with these structural frequencies, these structural resonances. There's another one surely in there that I can put on with another cursor. As the forcing function coincides with these structural resonances, then I clearly get more vibration as a result of that, what we would refer to as, it's hitting a resonant frequency. So I'll just close that workbook. Now go back to the signature testing advanced. And this is where it gets very interesting. So signature testing advanced workbook. Now I'm not going to be using the impact hammer channel any longer, and I've made a project here before called fan tracking. I'll take some of the effort out of setting these workbooks up from scratch. It takes a few moments to load, and in the meantime I'll start the fan. We put it on the second speed, and as you can see from the tracking setup sheet, that speed is around about 1300 RPM. And so what I've defined here is to do a rundown measurements from 1250 RPM to 100 RPM in 50 RPM increments. Now that requires that the rundown is sufficiently slow that at each of these increments in RPM, at 1250, 1200, 1150, 1100, I've got enough time to create a new spectrum with the required resolution of that spectrum, and I've defined that information in the acquisition setup sheet. So in the acquisition setup sheet, I've defined a bandwidth of 1024 Hertz with a resolution of 2 Hertz. That's 512 lines. That's going to result in half a second per FFT. So if this ran down very slowly, those half seconds would be quite heavily overlapped. If it runs down more slowly, then I can potentially have even finer frequency resolution. But I found that half a second with 2 Hertz resolution is reasonably good. Here in the time domain, here in the scoping sheet, you can already see some of the interaction of the various forced frequencies in this system. This is vibration being measured by the accelerometer over here. I can see it moving at a relatively low frequency, probably around this 11 Hertz. I could indeed use the stroboscope in the same way that I used it to freeze the fan motion, to freeze some of these vibrations if I found the appropriate rate at which that needed to flash. That's another legitimate way of estimating vibration based on the displacement of the system. Here I'm using the accelerometer. So I'm going to now go to the measure sheet and I will collect these spectra. So if I arm the measurement sheet, I haven't defined any particular display here, but I could create a display and populate that. Now I've armed the measure sheet. We're sitting here waiting to do a rundown from 1250 to 100 RPM in 50 RPM increments. So now we're sitting here armed and ready to start the acquisition, and if I press the stop button here on the fan, you'll see that at some point it drops through 1250, and you can see here the tracking RPM is progressively running down from that 1300 RPM to about 150 now, and there's one average left to do in a moment. We'll get the 150 RPM measurement, then the 100 RPM measurement is coming now. The rundown is complete. Would you like to save these data? Yes, we'll save those data. Disarm the system. Go back to the navigator here where I've already been looking at previous measurements that I've made. Here in this rundown folder, the latest run is run number 5. You can see some of the information I've got in here. I've measured the throughput, so I've got all of those time data here for essentially the vibration measurement. So that's currently on a real axis. If I change on an amplitude, I can see actually when I push the start button there's a bit of a spike perhaps here as it starts to run down, and then it runs down pretty quickly over, this is 26 seconds in total, so this is this is 10 seconds, this is 20 seconds, so these ticks are at 2-second increments, so it runs down within about 5 or so seconds, and then it starts to sort of slowly, return to rest. And you can still see some of the interplay of those various frequencies, even at that stage. I've got a tacho measurement here as well, actually, that I can put into here. If I remove the first curve, that's my tacho measurement. You can see there the RPM, which was sitting steadily at around about 1300 RPM. At the moment that I hit stop, it drops to 0. In fact, if I put the vibration measurement back in on the back of that axis, I can see those two measurements alongside with one another, which is quite a useful way to present that information. And you can see it wobbles around, down at around about 100 RPM for quite a while here before it comes to rest. Going back to the waterfall measurement, this is the collected FRFs. You can see them here in this display here. If I drill through to the auto power here, there are those 20 or so, 24 FRFs at each increment given here, which is an approximate RPM for the target RPM. So it's not always the case that we get, exactly 100 RPM. It's 107.69, and that's the center of the RPM. So that's, the data are collected either side of this particular RPM, 100, 150, etc. Remembering that they're collected running down rather than running up, but they're presented from low RPM here up to higher RPM, and if I drag those into this waterfall display, that updates, as you can see there. So the RPM axis is this one going sort of back here in this dimension here. I can actually add on some, if I turn on these options, I can turn on some ticks annotation. I can make, you can see there quite nicely that I've got 100, 200, 300, 400, 500, etc. up to 1300 RPM. There isn't actually a plot at 1300 RPM, that's just the axis at the back, at the very back. This curve sits just in front of that axis. As well as setting up the axes labeling and turning on the tick numbering, I've added some cursors in here. So if I right click on the display, I can add a harmonic cursor as an order cursor. That's what I've already done. In fact, actually, I haven't done that on this one, so I can add that in. I'll add that in on here. If I double click the first order, I can move that to 1, and you can see that there are now 2 order cursors at 1. This is 2. 3 was already there as well, so now I've got 2 at 3, 4, 5, 6, 7, and so on. I've also got some fixed frequency cursors to coincide with those values that I extracted previously for the resonant frequencies, the structural natural frequencies of the structure. You'll remember that I saw there was a structural resonance at 11 hertz, at around about 38.3 hertz, 153 hertz, and so on. I'm just going to remove that other harmonic cursor because it does make things a little bit cluttered. 11, 38.3, 153 approximately. And what's really interesting in the way that these data are presented is that, as you can see, there's lots of extra vibration along the 1 times order. That's because there's a lot of imbalance in this system, so there's always lots of vibration at 1 times. But when it coincides with this 11 hertz structural resonance, we get super high peaks. So those peaks in this region here are where the first order coincides with the 11 hertz resonant frequency. You can see similarly for the third order, when that coincides with this particular natural frequency at 38.3 hertz, I get some higher order peaks. And again, that actually at the top here is where the second order cursor, the second order coincides with 38.3 hertz. And over here, similarly, if I was to open this up perhaps to 6th order, we'd start to see some of the interactions even with this 153 hertz resonant frequency at these higher orders. It's not a brilliant way to review these data on a waterfall plot. It's quite a historical way to review them. Nowadays, with the extra computational horsepower we've got available to us, colour maps or Campbell diagram is quite a more meaningful way to present these data. And now we're essentially looking down from above on those spectral data. And so we've got spectra here at 100, 150, 200, 250, etc. It interpolates between them for the sake of colouring in the colour map. But you can see quite nicely that we get higher energy levels where the first order in this case coincides with this 11 hertz frequency, and where the third order here, that's the third order harmonic, coincides with this 38.3 hertz, and the second order here a little bit higher in RPM. There's a very strong order here, that 153 hertz approximately peak that we saw in the spectrum that we extracted using the modal impact hammer, the FRF. That one, because it's higher in frequency, many of these higher orders it coincide with that. And so when we, for example, see our 8th order, 9th order, etc., there's quite a lot of opportunities, 10th order, for that and for that excitation to occur. And we see there are some of the frequencies that I didn't really investigate that closely. I think there certainly was one at around about 100 hertz. I added that in. But this is the kind of information that we're able to extract using these kinds of techniques, and the explanations for the way that these data appear. You know, in as much as that this 11 hertz peak, for example, in the frequency response function for this structure, it didn't have a huge level compared with some of these higher order levels, but when the forcing function coincides with that natural frequency, then we really see the vibration level increase, and that's the meaning of resonance. That's why we look at vibration data on a logarithmic scale on the y-axis, because even the smaller peaks can be important when we drive the structure at those frequencies. That's everything I have for this particular video for now. Thank you for watching. I hope that's been useful. I'm Ben Holken, Associate Professor in Mechanical and Mechatronic Engineering here in the Faculty of Engineering and IT at UTS, and see you next time.